Yeah, so I don't know what I did. I'm just going to do it again. So we take the first case, which is, the set 1, and a non-empty subset of the set 1 is precisely equal to 1. And this set has the largest element of 1, which means the hypothesis is true for n is being 1. Now we check the hypothesis. We assume the hypothesis is true for of all n less than n plus 1, and then we check it for n plus 1. So it's true for all Sn, right? Now we take a subset of Sn plus 1. Now if n plus 1 is contained in B, then n plus 1 is the largest member. And if not, and we only have two cases by some axiom of set theory, but it makes intuitive sense, right? A member is either in B or not in B. So in this case, we can safely conclude B is a subset of Sn, right? And since the hypothesis is true for Sn, then we're done, right? So the set for which the set of natural numbers n such that for any subset B of Sn uh, has the property of having a largest member. So I'll just, it's a whole line, is an inductive set. That's what we have shown, right? It one is in the set, and if n is in the set, then so is n plus one, right? And it's an inductive set of natural numbers because we're already checking for natural numbers, right? So what does that show? That shows by the principle of induction that this entire set is the set of natural numbers. The set of natural numbers such that any subset of a slice of for a fixed for that natural number has the largest element. So this is an inductive set of natural numbers, and therefore this is precisely equal to z plus, right? So that's what the argument is, how it's going. Okay, so now what? Have we shown it? Yep, that's exactly what we had to show. So for every fixed natural number, we have this property. Yeah, is yeah. So now we have to show why this argument doesn't hold for z plus, right? So I'm going to show two proofs for it. One is a proof by counterexample. Uh, let's say the set z plus, which is a non-empty subset of z plus, right, has a largest member, right? We know it doesn't have a largest member in the reals, and therefore it's a counterexample. So that's one proof, right? Just the same proof as the book. Now for the other proof, we'll follow why the book is wrong, right? Yeah. So in the book, what it does is we take a subset B of Z plus, and then we take a slice Sn intersection with B, right? For let n belongs to B. Then we take this. Would it be a slice? It would be an n plus one here. Yeah. We take the slice. The smallest member in this set is not going to be the smallest. The largest member of this set is not going to be the largest member of this P. And that's precisely why the argument isn't carrying through. So yeah, we have a counterexample, and this is the critical step where it's being violated. So that was 4B. Okay. Yeah. So that's what the argument of the book is doing. Now, question 5A. Yeah, so it's going to be a similar argument. We have to show that given A comma B in Z plus, A plus B is in Z plus, right? So I'm just going to follow the hint of the book. So it says that X such that X belongs to real numbers. So this real numbers is the total set from which we're taking a subset, but we're eventually just going to have X in integers. So that's going to be fine. And A plus X belongs to Z plus is inductive, right? That's what we have to show. So does 1 belong to the set? Yes, and that is because Z plus itself is inductive. So A belongs to Z plus, since for all A belongs to Z plus. right? This was given to us. Yeah. A belongs to Z plus implies A plus 1 belongs to Z plus by the definition of Z plus being inductive, right? And us proving the property that any intersection of inductive sets is inductive, right? Now, now we have to show that it's inductive. So let's assume A plus B is in Z plus. Now, by Z plus being inductive, this means A plus B plus 1 belongs to Z plus, right? And this implies A plus B plus 1 belongs to Z plus. So what does that mean? That means the set of B in R, which and B is a real number here, such that A plus X is in Z plus, is indeed is an inductive set. That proves it. Now we have to show it's an inductive. Okay, now what? So this is an inductive set, right? And B is B. Yeah. So the argument now is a little bit subtle. So let's see. So now that we've shown that this is an inductive set for all n integers, what does that mean? That means so Z plus is a subset of this set, right? Because it's an inductive set of real numbers, right? And so that means if B belongs to Z plus, right? B belongs to let's call this set S, which implies anything that S satisfies, B will also satisfy. So that means uh, B belongs to R, which it does, right? And A plus B belongs to Z. So I'm invoking the property that, if something's in a set, then it will show the property of the set. So the property of the set says that X or B in this case, plus A is in Z plus. So what does that mean? That means B and A in Z plus implies A plus B in Z plus. So that's the argument. Okay. And the next one is also pretty similar, but it's slightly easier because we can just use the part A for it. So A comma B belongs to Z plus implies A dot B belongs to Z plus. So by a similar argument, we take the set of X, says that it's a real number, and A dot X belongs to Z plus, and we show that it's an inductive set. So it's going to be the same argument here, right? And Z plus will be a subset, and since B will already be a member of Z plus, then it's a member of this set, and therefore it's going to satisfy the property. So that's exactly what we're doing here again. So one belongs to S as A dot 1 is equal to A, which belongs to Z already, right? That's fine. Now, suppose A dot B belongs to Z plus, then A dot B plus 1 is equal to A dot B plus A, and A dot B belongs to Z plus by hypothesis, and A belongs to Z plus by also by hypothesis, this one, right? For a fixed positive integer A. And by A part, this means that A dot B plus A belongs to Z plus, since it's the sum of two positive integers. And that means B belongs to S implies B plus 1 belongs to S, right? So what does that show? That shows that S is an inductive set, and then the argument follows precisely as done earlier. Okay. What's the next one? Yeah. Okay. Hang on. What is? Okay. Yep. We're going to do the exact same way. Okay. So A belongs to Z plus, and x, x is a real number, and x minus 1 belongs to z plus union 0. Yeah. So 1 belongs to S because 1 minus 1 by definition is equal to 0, which belongs to the set containing 0. So we're fine. And if X belongs to Z plus, no, if X belongs to S, yeah, X belongs to S implies X minus 1 belongs to Z plus union 0. So then we'll go with cases. Since it's a union, so if X minus 1 belongs to 0, uh, so first observation is that 0 and z plus are disjoint here, right? So either x minus 1 belongs to 0 or z plus. So we'll have two separate cases and they're completely different cases. So if x minus 1 belongs to 0, then x minus 1 is precisely equal to 0 by set theory. And that means x is equal to 1 by the algebraic properties we proved earlier. So 1 is an S, so that means what have we shown here? X is equal to 1 and x is an S. Hmm, so this case has no contradiction. I guess that's it, right? Oh, okay, yeah. We have to show that x plus 1 is an S, right? So which implies x plus 1 is equal to 2, which implies x plus 1 minus 1 is equal to 2 minus 1 is equal to 1, which belongs to z plus, right? And x plus 1 also belongs to reals. Why? Because 2 belongs to real numbers, and that's because by the properties of the real numbers. So what does that mean? That means for the first case where x minus 1 is in 0, we've shown that it's inductive, right? Yeah. So because it's satisfying the property of S. Now we have to show for the other case that x plus 1 is also a member of set plus. No, S. So this implies x minus 1, yeah, x minus 1 belongs to Z plus. Now by inductivity of Z plus, we get x plus 1 minus 1 belongs to Z plus, right? Now that implies that x belongs to Z plus. Or are we done? I think we are done since Z plus is inductive, then x plus 1 is also inductive, pretty much. So we don't need this part. We just need x plus 1 belongs to Z implies x plus 1 belongs to S, right? So what this is actually minus 1 plus 1, but this is equivalent to saying x plus 1 minus 1 belongs to Z plus, right? Okay, so that shows that the set S is satisfying this property is inductive, and therefore, since A is a subset of Z plus and it's a subset of S, it will satisfy this property as well. It's the same argument. Now, yeah. So now we're having the whole of integers instead of just the positive ones. So C comma D belongs to Z implies C plus D belongs to Z and C minus D belongs to Z, right? Okay. So hmm, the problem was a lot simpler. I wasted way too much time on this. Yeah, this is it. We don't even need this. We don't need anything. This is how you do it. So First, you show that one is an S, right? Zero is an S, fine. That's true because identity is, C belongs to Z if and only if C plus zero, C minus zero is equal to C belongs to Z. So zero is an S, whatever, fine. Now one is an S because let's see, C plus one. What was it? Yeah, yeah. So this is where the critical hard work comes from, and let's just go with it. Let's see. So so if C is greater than zero, then C plus one belongs to Z plus, which implies C belongs plus one belongs to Z, right? Since it's a subset, and C minus one belongs to Z plus union zero, which implies C plus one belongs to Z, right? C minus one belongs to Z. So that's fine. If C is less than zero, then C belongs to Z if and only if minus C belongs to Z, and minus C in this case is greater than zero. So you just do the same thing here, right? So what does that mean? That means, yeah, essentially minus C minus one belongs to Z, right? Why is that? That's because here C is positive, right? So this if and only if C plus one belongs to Z, so we're done. And for this one, minus C belongs to Z plus, which implies minus C plus one belongs to Z plus by inductivity, which implies C minus one belongs to Z, and we're done, right? So one is an S. That is very clearly established. And now comes the kicker and why the solution is very, way more efficient than I thought it was. So let D belongs to S, which implies C minus D, comma C plus D belongs to Z. Now, since one is an S, this implies C minus D minus one, C plus D plus one, and minus C minus plus D plus one minus C minus D minus one are all in Z, right? So I'm using two things here. This is in Z if and only if C minus C plus D, comma minus C minus D are in Z, right? And since one is in S, that implies that all of these are in Z, right? Since this is true, this is also true, and since both of them are true, this is true. By since all of these, both of these, no, all four of these are, yeah, all four of these are in the set of integers. Okay, now comes the meat of the proof. So this implies this if and only if C plus D plus 1. So I'll just erase the unnecessary ones here. This is not needed. Oh yeah, right. Just put minus 1 here, right? C plus D plus 1, comma C minus D plus 1. R and Z. So what does that mean? That means, hang on, something's off. Oh yeah, not this. Minus C plus 1. Yeah, fine. Or C minus D plus 1. So that means D plus 1 is in S, given D is in S. So we just showed that this is an inductive, and given that D is in S, if and only if minus D is in S, which is easily verifiable, right? We get that all these things combined imply S is a superset of the the integers, and since D is a member of the integers, it satisfies this property, and we're done. Yeah, it's still long, but I wasted too much time on this. Okay, next part should be easy. Let's see. The set of all x. Okay, is that it? Yeah, okay. So C dot one is belongs to Z. All right, so one belongs to S. Okay, what else? Uh, Now if C plus C dot D belongs to Z, then C dot D plus one is equal to C plus D plus C dot D plus C, which we don't care whether it's positive or negative. Either way, it belongs to Z by the previous problem. So it's inductive, and C dot D implies minus C dot D. Yeah, minus C dot D belongs to Z, which implies C dot minus D belongs to Z, which implies if D is an S, then so is minus D. So yeah, that proves the final part. Oof, that was hard. Okay, we have to prove the law of exponents now, right? So a to the power 1 is equal to a to the power n plus 1 is equal to a to the power n dot a. So that definition is fine. Now, let's see. So for a fixed n, is it defined on natural numbers? Yeah. A n plus a to the power n plus 1 is equal to a to the power n dot a to the power a is equal to a to the power n dot a to the power 1. So what do we get? We get the first. Yeah. So it's true for n is equal to 1, right? This law. I mean, if you really want to write it down, we can write it this way. Uh, right? Okay. So we have to show this set is inductive now. Since one is in this set, and let's see. Yeah, a to the power n plus m is equal to a to the power n dot a to the power m, and a to the power n plus m plus 1 is equal to a to the power n dot a to the power m dot a by definition in the first step, this one, and this is equal to, let's see, yeah, a to the power n dot a to the power m plus 1. So m belongs to S implies m plus 1 belongs to S. So it's inductive. So the first law is proved this way. Second law, okay, a to the power n to the power m is equal to a to the power n m, right? So a to the power n to the power 1 is equal to a to the power n by definition of what the first power is. And is equal to a to the power n dot 1 by definition of what 1 is, identity, right? So 1 is in the set, and a to the power n to the power m is equal to a to the power n m, a to the power n to the power m plus 1 is equal to a to the power. So by the previous law, that's equal to a to the power m to the power m dot a to the power n, right? Now this is equal to this by the previous law, and this is equal to this by the previous law we proved. So this is by the induction hypothesis, this is by the previous law, and this is equal to this by the distributive property, and yeah, and this is equal to, yeah, this proves the hypothesis for the next stage, right? So induction. Okay, a to the power b to the power 1 is equal to a to the power 1 dot b to the power 1. So that's equal to a dot b, and that's equal to a dot b. So yeah, it's fine. Now a to the power b to the power m is equal to a to the power m plus 1 is equal to a to the power a dot b to the power m dot a dot b by the first law, right? Or is it, yeah, first law? And this is equal to a to the power m dot b to the power m dot a dot b. And by the first law again, it's equal to a to the power m plus 1 dot b to the power m plus 1, right? Uh, and that's exactly what we have to show. So yeah, very good. I showed induction rigorously so far, and I'm not going to do it ever in my life, hopefully. Yeah, these are the laws of exponents, and yeah. So define a to the power 0 is equal to 1, and a to the power minus n is equal to 1 by a to the power n, right? And we have to show that the laws of exponents hold for n and m being in integers. So they hold for positive integers. We just have to show the set S is such that D belongs to S if and only if minus D belongs to S, right? Okay. So yeah, essentially, okay. So one thing, what is given to us? A is not 0, right? If A is 0, we have a problem, but A is not 0. And we have full liberty to use the laws of algebra we just proved. So, hmm. So yeah, we just have to show this, right? Okay. Oh, hang on, hang on. I just showed it for a fixed n, right? Yeah, okay, okay, that's a problem. So for a fixed n, the laws of exponents hold. 1 second. Uh, okay, so we showed that for a fixed n, an dot a am is equal to an plus m. Now, by the commutative property of addition here and multiplication here, a to the power m dot a to the power n is equal to this. And for an arbitrary m, we have this being true, right? And yeah, so we go over all m and go over all n to show that for using the same property argument that for m and n belonging to z plus, the laws of exponents hold. And the same argument extends to all of the laws of exponents uh, for this case. Okay. Now we have to show that 0 is satisfying the law of exponents. So to show that, yeah, a dot b whole to the power 0 is equal to 1 is equal to a to the power 0 is equal to a to the power 0 dot b to the power 0. So we're good. 0 is also in the set. And by a similar argument, all of them are also following it. So n comma m belonging to z plus union 0, it's true, right? So yeah, I'll just write it down. X belongs to R. X at yeah, a to the power n dot a to the power x is equal to a to the power n plus x, and so on, right? And we're switching them, and by switching them, we're getting the x to be filling in both categories, right? So yeah, we're using that the laws are equivalent in both directions. So using this, uh, we're showing that this set is the set of all integers at least. So it's inductive, it contains the negatives and zero. And then we're flipping it to show that it's applying in the other way too. And from that, we'll be able to show that it's true for the integers. So I'm not going to write this anymore. Hopefully, I might end up writing it again. Yeah, it's a lot simpler. So it's a lot simpler. So a to the power n minus m dot a to the power m. So we're taking the case that m is less than n here, right? So this is positive and this is positive, and therefore we can use the laws freely, right? And same thing with m is equal to n. We can also use the laws freely because it's just identity, so we're fine. So in both these cases, a to the power that's equal to a to the power n minus m plus m by the law we just proved. Now this the laws of addition hold here. So as a result, we get a to the power n. And now we just have to multiply by a to the power m inverse on both sides. So a to the power n minus m is equal to a to the power n dot a to the power 1 by a to the power m. And that by definition is equal to a to the power n dot a to the power minus m. So the law holds, right, in these two cases. Now we take the final case of n minus m is less than 0, right? So a to the power n minus m is equal to 1 by a to the power m minus n, where it's greater than 0 now, right? And so this is greater than 0. What else? Dot 1 by a to the power n. Okay, so essentially I can do that freely because so this holds by definition of the what the negative thing is, and this is positive. So yeah, and this is also positive, and this we and I'm just multiplying on both sides here, right? Yeah, should be fine. Yeah, this is equal to 1 by a to the power n dot a to the power m minus n by the laws we've proven, and this is equal to 1 by a to the power m by what? By the law on only this part, right? And that's equal to a to the power minus n, right? Now, now we can multiply on yeah. Now we multiply by a to the power n on both sides. So a to the power n minus m is equal to a to the power n dot a to the power minus m. And this is for the case where n minus m is less than 0. So essentially, I use the inverse laws we've shown, and since a and b are both will come to me later, a is non-zero, the law holds. So it what I've shown now is that if D belongs to this set S such that the properties hold, then so does minus D. And the equivalence follows because minus of minus D is D. Okay, so let's prove the other laws. Yeah. a to the power, so n to the power 0 is equal to 1 is equal to a to the power 0 is equal to a to the power n 0. So again, follows on the identity thing, and it's true for all n, including 0. So we've at least shown that it's true for z plus union 0, right? So identity case is trivial. I'll prove it for the last step too. A dot b to the power. Oh, I just showed that. Yeah, a to the power 0 dot a to the power 0 is equal to 1 dot 1 is equal to 1 is equal to a to the power 0 is equal to a to the power 0 plus 0. I mean, if you insist, right? So it's not a big deal for the identity case, or I mean, in this case, zero case, right? So a to the power n to the power minus n, right? Okay, now we have another problem in the sense that we can't flip it like we did for the other. We can't flip it that easily, right? Yeah. Hmm. Or maybe we can. Let's see. So I'll just see if we can flip it right now, right? So if this is equal to a to the power n into minus n is equal to a to the power minus n into m is equal to a to the power m into minus n and is equal to a to the power m to the power minus n by the law we've proven. So yeah, if we prove it for a fixed n, we can indeed switch. So it doesn't matter how we do it. We can use integers or whatever we want. So the flipping is fine. Essentially, we're exploiting the symmetry of this problem. Okay. Now, a to the power n to the power minus m is the same as 1 by a to the power n whole to the power m, right? Okay. Now, does the power transfer inwards? That's the question. Hmm. Hmm. Okay, so a to the power n to the power minus m is this by definition of what minus m is, right? So m is being assumed to be a positive integer here or identity, doesn't matter. And this is equal to a to the power nm by definition, by the power law for both being positive, right? And n is a fixed integer, but later I'm going to show that it doesn't matter here, right? Okay, now let's see. Yeah, this is equal to what we have to show. Yeah, a to the power nm minus by definition, right? By definition of what this means, and this is equal to a to the power n into minus m by the laws we've shown. And that's precisely what we have to show. Okay. Yeah. Okay. Now a dot b whole to the power minus m is equal to a 1 by a dot b whole to the power minus whole to the power m. No, not making this mistake again. Yeah. And that's equal to 1 by a to the power m dot b to the power m, right? Now this is equal to 1 by a to the power m dot 1 by b to the power m by the laws we've shown. And this is equal to a to the power minus m dot b to the power minus m. Yeah. So what have we shown now? We've shown that for the laws, the set of real numbers satisfying the laws has this property, right? And it's inductive. And 0 belongs to S for a fixed integer n. So it doesn't really matter that, yeah, for most of my arguments, either n has to be an integer or a real number. But other than that, it doesn't matter, right? Maybe non-negative. No, even non-negative is fine. A and B need to be non-negative, right? So given A and B are non-negative, and for all any arbitrary fixed integer, these laws are fine. And to summarize the final step, I have also shown that if we flip the n and m, right, the law is equivalent. So if we show it for n or m being varying, it won't matter because we can switch it around given the symmetry of the situation. So what does that mean? That means for any fixed integer this law holds, then it's if the same as saying m and n are. So we're showing it for m actually, but it ends up being the case for n as well, right? And that's because we can uh, write an equivalent statement of the law. So yeah, that's the whole summary, and I'll have to edit it properly to make sure it's presentable. But I think I've shown everything I can. Okay. Yeah, question eight, A part is trivial because R has LUB implies R has GLB. Because in general, if it has the LUB property, then it will have the GLB property for any order, and R is having an order. So yeah, that's fine. Yeah. So infimum of is it this one or yeah, it's set. Okay. 1 by n belongs to Z plus. Yeah, is equal to 0. Right. So I'm going to do the analysis trick again, and it works for infimums, right? Okay. So let's see. So 0 is less than equal to 1 by n for all n belongs to Z. That is true because n is greater than 0, which implies 1 by n is greater than 0. We've proven this using algebraic properties, right? And this is the same as n inverse. I'm using them interchangeably now, right? So that's one thing. So what does that mean? It means infimum of, I'm going to call it S, is so this is lower bound of the set, right? And we want the greatest lower bound. So it's going to be greater than equal to 0, right? That's what it means. Okay, now we have to show it's less than or equal to 0. If it's then we can use the analysis trick, which I showed earlier because yeah, it works. Okay, so we have to show it's less than equal to 0. So let infimum S uh, be greater than 0 strictly, right? Now, so let it be equal to epsilon, fine. Okay. How do we show this? Yeah, so I'm not allowed to use density just yet. So, hmm, okay, so let's assume we have an epsilon that's greater than 0. That's the lower bound. That's the lower bound of the set, right? And we have to arrive at a contradiction. So epsilon is greater than 0. Epsilon is a real number. So I guess I'll write it properly, right? Okay. Yeah. So that means 1 by epsilon is also greater than 0. That's because of what we've shown. That was for all real numbers, mind you, what I've shown that time. Okay. Now, yeah. So epsilon is less than equal to 1 by n for all n by n. N belongs to z plus, correct? By our assumption. So that means since epsilon and n are both positive, we are free to do this substitution that n is less than equal to 1 by epsilon for all n belongs to the plus. And this is the same thing as saying that 1 by epsilon is an upper bound of all integers, and that's not possible. And that is the contradiction because of the argument. If this is the least upper bound of n, right, which is pretty much exact, it's an upper bound, then yeah, and so we have to exploit the least upper bound thing. But yeah, so any subset of the real numbers does have a least upper bound, and yeah, either way we've shown. Hang on. Yeah, so the set of integers doesn't have an upper bound because then it has a least upper bound, and then we'll get a contradiction. So this is false, and therefore any epsilon greater than 0 cannot be the infimum. So infimum of s is less than equal to 0. And from both of them, we get that infimum of s is exactly equal to 0, right? Okay. Yeah, sorry for taking a huge break. Not that you would know, but yeah. I just solved question 8C just in case I didn't actually solve it because I'm not sure if I did. So I hope you can hear me. Yeah. So first I'll show by induction that 1 plus h whole to the power n is greater than equal to 1 plus nh. So it's true for n is equal to 1 trivially because they're equal. Now 1 plus h to the power n plus 1 is greater than equal to 1 plus h to the power n dot 1 plus h, which is greater than equal to 1 plus nh dot 1 plus h. So, we're multiplying by the same number, and this is greater than equal to 1 plus nh plus h plus nh square. Now, since h square is greater than 0 for all h belongs to real numbers, and n is greater than 0 as n belongs to z plus, and h square is greater than 0 equal to, yeah, h could be 0. Nothing's stopping us, right? Yeah, there's nothing stopping us. No, it is stopping us, but fine, whatever. And because of that, we get greater than equal to 1 plus n plus 1 h. So yeah, we showed it by induction. Now, yeah, a is greater than 0 is given to us. So by induction, a to the power n is greater than 0 as a to the power n plus 1 is equal to a to the power n dot a, which is the multiplication of two positive quantities and therefore greater than 0. Yeah. Okay. Now, what else? So therefore, infimum of a to the power n is going to be greater than equal to 0, right? Or is it less than equal? 0 is the lower bound, so it's going to be less than equal to 0. No, greater than equal to 0. Yeah. Now it's less than equal to 0, and for that we'll show that, yeah. So 1 plus, yeah, we take h is equal to 1 minus a by a, which implies since a is less than 1, I believe, is it? Yeah, and greater than 0. H is greater than 0, right? So that means 1 plus 1 minus a by a whole to the power n is less than equal to 1 plus n into 1 minus a by a. Yeah. And this happens to be equal to 1 upon this. And this is equal to a to the power minus n, as it's equal to a to the power minus 1. So it rearranges, and this is less than equal to, what is it? Let's see, a plus n into 1 minus a by a. Yeah. And yeah, so now we rearrange it. We get a to the power n is greater than equal to, yeah. Uh, or is it less than equal to? Let's see. Oh, yeah, it's less than equal to. Unless, oh, yeah, sorry. Yeah, yeah. So is less than equal to a upon a plus n into a minus 1, 1 minus a. Yeah, okay. And yeah, so I'm leaving it as an exercise, but infimum of a dot bn is equal to a dot infimum of bn, and infimum of bn is greater than equal to bn greater than equal to cn implies infimum of bn is greater than equal to infimum of cn. Yeah. Okay. So given these two theorems, and to prove them, this one is easy. You just use the definition of infimum. So well, it's going to be greater than equal to infimum of Cn, right? And this, uh, and infimum of Bn has to be smaller than that, right? Now, Cn is okay, infimum of Cn is a lower bound for Bn, and therefore infimum of Bn is going to be greater than equal to Cn, as it's the greatest lower bound. So we're done for this one. And for this one, yeah, you just use the definition of lower bound, and essentially Bn is greater than equal to some constant C, which implies A dot Bn is greater than equal to A dot constant C. So this C happens to be the infimum of Bn, and that's how we get the theorem. Now, because of that, so you'll have to write the precise generalization of this theorem, but essentially what I'm going to use it here is that, well, infimum of An is less than equal to in A dot infimum of 1 upon a plus n into 1 minus a. Yeah. And the infimum of this is going to be 0, right? And that is because of, so yeah, 1. Yeah. So how do I show it's 0? Let's see. So we have it for 1 by n already. And yeah, you just need to show this is greater than equal to 1 by n into some constant c, and then from that you get 1 by c into 1 by n infimum. So yeah, you need to find that constant c here, and from that you'll get 1 by c into 0, which is equal to 0. So yeah, and from the 2 we'll get infimum of n is exactly equal to 0. All right, so now we encounter the question that I spent 3 hours on, at least. Yeah, and the whole reason is because I could not use the fact that we're using a subset of the integers, and to use that, we need to we need to use the well ordering principle. There's no other way. And yeah, because working with a set of integers, not just any ordered set, right? Yeah. So we take a subset of the set of integers, right? And it's bounded above. So there exists the least upper bound B, right? Now we have to show that M has the largest element, right? So if we show B is an M, we're done, right? And that's precisely what we have to show. So B has to be equal to some member of N, and since B is an upper bound, it's going to be a largest element too. So yeah, okay. It's a trivial exercise to show that the largest element is an upper bound. So because of that, it follows from the definition, and therefore we just have to show that. Yeah. Okay. Now, yes. So B is greater than equal to M for all n in M. Yeah. Now we need some excuse to show that there exists an n belongs to M such that n is less than equal. Right. Then it'll be done. So to show that, there are two things. So we take the set of all n belonging to integers, positive integers, such that n is greater than equal to p minus m, right? And so this is a non-empty set because there exists an n belongs to m such that n is greater than b minus 1, which implies 1 is greater than b minus n. And so 1 is definitely in the set, right? And since it's a yeah, since it's a non-empty set of positive integers, it has the least member by the well ordering principle. So this is where it's used, and this might be the only place it's used. Yeah. And yeah, so this P has to be less than equal to 1 since 1 was a member of it, right? I just showed that. So we have, since it is a subset of the set of positive integers, right? P is equal to either 1 or 0. So we'll take the case that P is equal to 1 and arrive at a contradiction, and then we'll show that P is 0, and that's exactly what we have to show. So yeah, now let P be 1, then that means P minus M is greater than 0 for all M in M, right? And since this is positive and 1 by 2 is greater than 0, as 1 is greater than 0, which we've proven, and 1 plus 1 is greater than 0, which is exactly what 2 is. And since 2 is positive, 1 by 2 is positive, right? So half is positive, and so is B minus M. And therefore, their product is positive. So B minus M by 2 is positive, right? And that implies B plus M by 2 is minus M is positive for all M in M, right? So what does that mean? That means we've actually gotten a set of upper bounds of the set M that are lower than B. That's what we've gotten, right? Because B is strictly greater than B plus M by 2, and this is strictly greater than M. If B is greater than M, which it is by assumption. So yeah. So what have we gotten? We've gotten a class actually of upper bounds which are lower than B. And this contradicts the fact that B is the least upper bound of this set M. And because of this contradiction, this assumption is wrong, right? So how do we negate this statement? We say that there exists an M belongs to M such that B minus M is less than equal to 0. So M is, so yeah, we can choose M here, doesn't matter. right? And since this is the case for all of them, so we have there exists n belongs to m such that n is equal to b, and b is the least upper bound. So yeah, we have a largest element. And this I spent 3 hours on. I'm not kidding, just because of the well ordering principle. So yeah, this exercise will show you why you can only tackle integers with the well ordering principle, nothing else. Okay, hang on, let's check the thing. Oh, I hope I don't block it. I really hope I don't. Yeah, let's hope I don't. Okay, B part. Yeah, so the next part gets easier because they just use the A part. Yeah, so we there exists n belongs to Z such that n is greater than x. Uh, X is not a member of integers and greater than n minus 1. Okay, now we take the set of all integers such that x is greater than n minus 1. Now, since x is an upper bound of this set, this is bounded above, and therefore this has a maximum element, right? Let n let n be this maximum element, right? By part A. Okay. Now n will be greater than x minus 1. Uh, Hang on. Yeah. So x is an upper bound, so x is greater than equal to n minus 1, or is it n? Yeah. Yeah, x is greater than n minus 1 for all n. Uh, Hang on. Okay, yeah, n is the least maximum member. Now, because n is the maximum member, n plus 1 cannot be less than x, right? Which means n plus 1 is greater than equal to x. Oh, sorry, not n, n minus 1 plus 1, right? Or sorry, more like n plus 1 minus 1. That's going to be n, right? But if n is equal to x, then x would turn out to be an integer. So n is greater than x. And that's also a problem. Yeah. Okay. Now for the next part, x minus y is greater than 1. So since x and y are, we have a couple of cases here. Let x be an integer, right? Then x is greater than x minus 1, and they're both integers, right? And that's greater than, which implies x minus 1 is greater than y, right? This is greater than y. So we've got an integer between x and y, that's greater. And if y is an integer, then y plus 1 is an integer since the set of integers is inductive, right? Yeah, you can show that if you haven't. I don't know if you have or not, but yeah, it's inductive. You can show it. And y plus 1 is less than x and greater than y. So we've gotten an integer between x and y, and it satisfies the criteria. So now we'll tackle the case where x and y are not integers, and x minus y is greater than 1. Okay. So there exists n comma m such that n is greater than x is greater than n minus 1, and m is greater than y is greater than m minus 1, right? Okay. Now this n has to be, so let m be greater than equal to n, right? And I want to arrive at a contradiction. Essentially, you know, x, y, uh, n minus one, m n minus one, something like that. So one of them is greater than the other. So x is greater than y, so it's left, whatever, and therefore n is greater than m, and that's what I want to show. So towards the contradiction, let m be greater than equal to m, right? Okay. So then what? Then m is greater than y is greater than equal to n greater than x. Is that right? Let's see. Greater than n minus 1 is greater than equal to m minus 1. Yeah, something like that. Once again. Greater than equal to greater than n minus 1. Greater than equal to n minus 1 is, yeah, that's less than. No, greater than x minus 1, right? Okay, so y is greater than x minus 1. That means x minus y is less than 1, which is wrong, right? Wrong. So that means n is greater than m. That's proven, right? Okay, so now what? Now one of them is going to satisfy the criteria that we want. So n might not do the job, n minus 1 might, or m might. Let's see. Hmm. Okay, so I'll try to show that n greater than m implies n minus 1 is greater than equal to m, right? If they're both integers, I'll try to show that. But given this, x is greater than n minus 1, greater than equal to m, greater than y, then we'll be done. So we just need to show this, right? Otherwise, the problem solved. So let's show this. Okay, n is greater than m, n comma n are both integers. Okay, so we take the set n of m. I'm just going to write p is n is greater than, yeah, we'll have a maximum element since it's bounded above. And yeah, so in this case, it will be n minus 1 precisely, right? Yeah, so why is it n minus 1? If n plus 1 is minus 1 plus 1 is equal to n, and therefore it's n less than equal to n, right? Or greater than equal to, yeah. And therefore, it is indeed the least maximum member of the set because it's contradicting the assumption, maximum integer. And it's a member of the set because one is positive, right? It is indeed a member of the set. So n minus 1 is indeed the answer. And that means n minus 1 is going to be greater than equal to all of the members of the set, which means it's going to be greater than equal to m, since n is less than m. And therefore, m belongs to, let's call it s. So n minus 1 belongs to s and is the maximum number. So, yeah. Because of this, n minus 1 is greater than equal to m. And I'm using a part here again, right? Yeah. Okay, let's do c part. Oh, d part. Okay, so let's see. Okay, x minus y is greater than 0, I believe. No, y minus x doesn't matter much. Yeah. Now, if n into y minus x is less than 1 for all n belongs to integers, then what? Then we have an upper bound, I believe. Um, so how do we show there has to be an n here? Tell me then. Hmm. But let's see. I don't know. Hmm. Okay, if that's the case, then hmm. Oh, okay, wait. Yeah, since it's positive, 1 by y minus x is also positive, right? So n is less than equal to yeah, less than y minus x, 1 by y minus x. And this is a bound for the set of integers, which is just plain wrong, right? And because of that, there exists, because of the contradiction, there exists n belongs to integers such that n into y minus x is greater than equal to 1, right? Otherwise, we're getting a contradiction. So that's the negation of the statement. Okay, that's one step. Yeah. Now I just got it m. Yeah. Okay. Now since my minus mx is greater than equal to 1, can I just write m plus 1? Fine. And hmm, hang on. Okay, since 1 is greater than 0, it's pretty safe to assume that hang on, yeah. So if this is the case, since 1 is greater than 0, I'm just going to add 1 into it. So then we'll get m plus m in m plus 1 into y minus x is greater than 1, right? I just want to be a little bit safer. Okay. And this is possible because 1 is greater than 0. Yeah. So m plus 1y minus m plus 1 x is greater than 1, right? Treat them as two numbers. Okay. What else? Now, by the earlier theorem, there exists an n such that m plus 1 y is greater than n is greater than m plus 1 x, correct? Did I just mess the whole thing up? Okay, it doesn't really matter, right? Just switch it around if you need. X, switch x with y if the question is copied incorrectly, it's fine. Yeah, okay. Now, we can just, okay, so m is a positive integer, right? And n plus 1 is also a positive integer as the set of integers are inductive. And that means that means it's positive, right? So 1 by n plus 1 is positive. And then therefore we can multiply by a positive number on the both sides and preserve the inequality. And therefore y is greater than n by n plus 1, which is, because it's by definition precisely that, and that's greater than x in the same way. And n by n plus 1 is precisely defined to be a rational number. So we're done. And yeah, the inequalities are flipped. But yeah. Okay. Yes. Question 10. So I'll just follow the hints because they're a pretty good proof. Okay. So x plus h whole square is equal to x square plus h square plus 2h, right? Now, is that given to be positive here? I believe it is. Yeah, it's okay, two cases. So if h is equal to 0, the implies the equality is maintained, right? So the statement is true. So I'm just skipping this case altogether. Now, h is greater than 0 and less than 1, right? Okay. So, yeah, h is greater than, sorry, it's h is equal to h dot 1, right? Which is greater than h dot h, as h is a positive number and 1 is greater than h, which is greater than h squared, right? So if h is greater than 0, then x plus h whole square, which is equal to that, is less than x square plus 2h plus, oh, sorry, x, yeah, plus h, right? Yeah. And what we get? In the case where this is true, x plus h whole square is less than x square plus h into 2x plus 1. And the equality holds in the other case. So the statement is still what the question. And in a similar case for the other one, I'm not solving the h is equal to 0, 1. And x minus h whole square equal, is equal to x square minus 2hx plus h square, which is greater than 0. And therefore, this is, yeah, x minus h whole square is less than equal to x squared minus 2h x, right? So that's a part. Yeah, yeah. So choose h to be, we'll find out. Okay. X square is less than a. X square plus 2hx plus h square. Sorry, plus h is less than a. We need to find an h greater than 0. So this is the case. And yeah, so h into 2x plus 1, right? Yeah. So choose x to be, since this is the case, a x square minus a minus x square is greater than 0, right? Yeah. So choose h and x is greater than 0, which implies 2x plus 1 is greater than 0, right? So h is equal to a minus x square by 2x plus 1 by, what should I take? 2 is greater than 0, right? And if you substitute this here, you will get a plus x square by 2, which is strictly less than a and strictly less than x square. Yeah. So this will be useful, but essentially we have h such that x plus h whole square is also less than a. And yeah, in a similar approach, yeah, x square is less than a, which implies x square minus hx. There exists an h such that this is the case. Is it? Did I switch it? Yeah, I switched it. Sorry. And for that, simply choose x square minus a by 2h, by 2x, or into 2. Yeah, and that will give you the same answer, right? Okay, so B part is solved this way. And essentially, the conclusion we've reached is that um, for any x squared less than a, we found an x plus h which is definitely greater than x, such that x plus h whole square is also less than a. And if x square is less than a, greater than a, we found an x minus h whole square less greater than a, and x minus h is definitely less than x. So yeah, that's the conclusion of P. Okay, so yeah, let P be the set of real numbers x such that x square is less than a, right? Now I'll take two cases here. One is greater than a, and one a is greater than equal to one, right? Or more like yeah, that's fine. Yeah. So in this case, a square is less than equal to one, right? Yeah, one is a bound of a, and by the transitive property, one is a bound of x square. Let's see. If x is greater than one, then x square is greater than one. This is easy to show by induction. Yeah, by this way because one is greater than zero, right? Therefore, you can multiply by a positive quantity, so x square is greater than one. So because of that, x square is going to be less than equal to one. Uh, yeah, so if one is equal to a, then we just get two. Two is a bound in this case, right? Just it works out. So two is greater than one strictly because one is greater than zero, and one is greater than equal to a, and one is greater than equal to x square because otherwise it will contradict being that. Otherwise, it will be greater than one, which will make it not a member of the set, right? So this is indeed bounded. Now, in the case where a is greater than one, let's see. So a is greater than one, case two, right? We have to find another bound. Okay. So for that, we get a square, I believe. A square is going to be greater than one, right? And more importantly, greater than a, right? Okay. And so if x is less than a, sorry, if x is yeah, if x is greater than equal to a square, or just a, yeah, fine. then x square is greater than equal to a square. You can just take anything you want here. You can, if you really want, you can try using power rules here and then greater than equal to one, and then use the theorem I just proved. Either way, this holds up, right? Many ways of showing it, and this will be greater than a, and that will be the problem because then it's not even a member of the set. So a will be a bound of x because we proved if it's not, then we get a contradiction. So a will be a bound on the set then. Yeah, if a is greater than one. If it's less than one, then two is a bound of the set. So yeah, and we have to show it's non-empty. That's also there. So again, if a is less than one, then how about a by two? So yeah, a by two should work, I think. Maybe. Hmm, let me think. Hmm. Now a is less than one, so a square has to be less than one, right? So a square by 4 has to be less than 1 by 4. Sorry, more importantly, less than a, right? Or is it more than a? No, it's only more than 1. Yeah. Hmm, that is a bit of a problem. Let's see. But yeah, if a is greater than 1, it's trivial, right? If a is greater than 1, then 1 square is less than a, and 1 square is equal to 1. So we're done here. But if a is less than 1, then we'll have to think. Hang on, is a given to be positive? Yeah, it is. Okay. This case, we just have to show in this case, the set B is not. Okay. Hang on, A square is definitely smaller than A, right? Oh, so A itself enough. A square is less than A. Is that true? Oh, yeah, never mind. Yeah. A square is less than A, so A itself is a member. So we're done. Yeah. Anything else? Uh, yeah. If B is equal to supremum of B, well, there are three cases. B square is, well, it's going to be either greater than A, B square is less than A, or B square is equal to A. And in both of these cases, we'll get another B plus H whole square, which is greater than A, and minus H, I believe, yeah. And B minus H will be less than B. B plus H whole square will be greater than A, less than A, and B plus H is greater than B. And both of these will contradict so this will contradict what will it contradict? Yeah, this will contradict that it's an upper bound, I believe. One of them will contradict it's an upper bound, and the other will contradict it's the least upper. Yeah, so this is a lower upper bound. So yeah, so this will contradict the least upper bound, and this will contradict the upper bound. but it's an upper bound. Yeah, because this will be greater than B, so it's a problem. And therefore, this is the only valid option by contradiction. Okay, yeah, that's one is easy. B comma C are both positive, and B square is equal to C square, right? So I'm going to show the we have to show this implies B is equal to C. So I'm just going to show B not equal to C implies B square not equal to C square, which is the same thing. So without loss of generality, B is greater than C. The other case is similar, which is going to be C is greater than B, but we'll do it. And by do it, it's in the generality. So since they're both positive, that implies B square is greater than CB. And this also implies BC is greater than C square. So by the transitive property, B square is greater than C square, which means B square is not equal to C square. And in the other case, we'll get the other inequality. It's the same thing. So yeah, that's the last part. And this shows the uniqueness of the supremum. So there's a unique number such that B square is equal to A for all A, which is a real number. That's what we have shown using the least one property. Okay, last question. So let's attempt question 11 now. This is a long video. Okay, we have the definition of odd and even, and m by 2 is not an integer here since m is odd. And we have to show m is equal to 2n plus 1 for some n belonging to integers, right? Now, by what we've shown earlier, there exists an integer such that n by 2 is greater than n by 2, and this is greater than n minus 1, right? And since 1 by 2 is positive, and 2 is positive, more importantly, 2n is greater than, yeah, whatever, is greater than m is greater than 2n minus 1, 2, right? Now, if we take the set of m that is greater than 2n minus 2, it's going to be, so from this, since the set of all elements such that, yeah, let's write it down, is, so both of these sets have maximum and least element, GLB and LUB. No, not the same thing, but you know, you can show it has the least element too. It's Yeah, it's a similar proof using the Vallotting principle. So, anyways, yeah, they both have maximum and least element because they're bounded above and below, below and above. You get the idea. And because of that, and okay, it's easy to see that the least element is here is 2n minus 1, and the maximum element here is 2n minus 1. And since m is in both of these, m is greater than equal to 2m minus 1, and m is less than equal to 2m minus 1. And therefore, it's precisely equal to 2m minus 1, right? And 2n minus 1 is equal to 2 of n minus plus 1 minus 1, right? Or is it something else? Yeah, minus 1, which is equal to 2n minus 1 plus 2 minus 1, which is equal to 2n minus 1 plus 1. And since n minus 1 is an integer, if n is an integer, and since n is an integer, this entire thing is an integer, and yeah, we've shown the question. Yeah. Okay, this is pretty easy. So P and Q, So P is equal to 2n plus 1 and Q is equal to 2m plus 1, right? And yeah, so P dot Q is equal to 2n plus 1 into 2m plus 1 is equal to 4mn plus 2n plus 2m plus 1 equal to 2mn m plus n, and m plus n is an integer, and mn is an integer, so and 2mn is an integer, so their sum is an integer, so this the entire thing is an integer plus 1. Hang on. Yeah, I just changed things. Yeah, and therefore P dot Q is odd and P is odd, so P is equal to 2n plus 1. P to the power n. So let P to the power n be odd. We'll show P to the power n plus 1 is odd, is equal to P to the power n dot P, right? Which is equal to 2 to the power. Oh, n is not a good idea. I'll just write that. Z plus 1 into 2 omega W plus 1. And since the product of two odd numbers is odd and P is odd, therefore this entire thing is odd. Odd, right? So yeah. Okay, yeah. So yes. C part. Now let a dash. Is that it? Yeah. Let A is equal to M by N and both of them being even. So M is equal to 2P and N is equal to 2Q, right? Okay. Yeah. So let N equals the least member of the set X such that X is a positive integer. Is that it? Yeah. And X dot A is a positive integer, right? Okay. So N dot A is equal to M by definition. Otherwise, A is not M by N, right? And we're assuming N is the least member. So we're assuming this here. So we just need the existence of one configuration where one of them is not odd, right? It doesn't matter if they, no. So we just want that for all is not the case. So if we find a single configuration where one of them is odd, then we're fine. So let's say for all of them it's even, and therefore to P dot A is equal to 2Q. No, Q. Yeah. Yeah. Now cancellation law applies. So Q dot A is equal to P. Now P is by definition an integer, and this contradicts the minimality of N. And therefore, because of the contradiction, and for all, yeah, so N cannot be even essentially. If M is even, then N cannot be N cannot be the least member and even at the same time. That's the contradiction. If A is rational. And this brings us to the proof that square root of 2 is irrational. So let square root of 2 equals M by N if it's rational towards the contradiction. So by definition, M by N whole square is equal to 2. That's the definition of square root of 2. And we establish the uniqueness and everything. And this thing is by definition M dot 1 by N whole square, and this is equal to m square dot 1 by n square, which is equal to, yeah, m square by n square. So any problem here? Let's see. Oh yeah, this is the law of exponents, so it's fine. Yeah, and so is this. Anyways, so they're both integers also and equal to 2, right? Okay, now 2n square is equal to m square. Okay, since n is an integer here, n square is an integer here, therefore m is even, right? It's equal to 2p, right? So m is equal to 2p, right? Since it's literally equal to 2p, p is an integer, right? So no problem here. Okay, now m square is therefore equal to 4p square, and since they're equal, n 2n square is equal to 4p square, so n square is equal to 2p square, right? And because of that, n is even, and this contradicts the earlier theorem. So n and m are m and n are both even, and this proves that this contradicts the theorem, and therefore square root of 2 is irrational. Hang on. Yeah, it's showing it for all configurations. There's no. This is a proof that m and n are even. Therefore, for all, you know, the reason this works is that because of all, this proves it in generality, not just assuming a special case, right? So yeah, yep, all right.